Our topic belongs to urban computing applications planning related, which explores how data-driven methods can support smarter urban planning and management. With rapid urbanization, cities are facing challenges like congestion and infrastructure maintenance. Traditional planning methods based on manual service can no longer meet the needs of dynamic cities. Urban computing provides new opportunities to use large-scale data such as GPS trajectories and sensor records to make city planning more efficient, adaptive, and sustainable. We contributed equally, and each of us reviewed 2 academic papers for this task. This paper studies how to plan bike line using rail-sharing bike data rather than traditional survey-based methods that ignore actual travel demand and budget limits. Effective bike line planning can reduce traffic congestion, improve safety, and promote sustainable mobility in urban areas. The authors propose a data-driven approach that formulates the planning as a constraint optimization problem. They designed a grid network expansion algorithm with a tunable parameter alpha to balance between covering more users and ensure longer continuous routes. They evaluated the method using 1 month of mobile trajectory data from Shanghai containing over 230,000 trips. The method increases the line coverage effectiveness by 10 to 20% compared to baseline heuristics. It successfully identifies major commuting corridors such as a Jingyun Road station, and the system recommendation were validated by Shanghai government officials. The algorithm's scalability and reliance on one city's dataset are limitation. Future work may include large-scale parallel processing, and this paper aims to improve the recycling efficiency of broken dockless bikes, which have become a major urban issue due to overuse and poor maintenance. Efficient recycling not only reduces resource waste and pollution, but also ensures the sustainability of urban bike sharing system. The author proposed a 2-stage data-driven system. The first one is a broken bike inference module that predicts the failure probability of each bike using its lifetime, riding frequency, and the trajectory features. The second one is scatter search-based route planning algorithm that optimizes focus recycling routes under time and vehicle capacity constraints. The model is trained and evaluated on mobile data from Beijing and Guangzhou, including over 1 year of trajectories and recycling logs. The proposed method achieves 97.6% prediction accuracy and improves recycling efficiency by 2 to 2.5 times compared to mobike's manual operations. The system is currently city-specific. Future work will extend it to multi-city deployment and integrate real-time traffic and multi-agent coordination.
This is the first paper that I studied. Illegal parking is a common urban problem, and traditional methods to detect it are either too expensive or require human intervention. So, the paper proposes a solution that makes use of bike trajectory data based on the fact that bike trajectory deviates from its path when a car is parked in the biking lane. The system is implemented using 2 components, and the whole system is based on shift distributions and KS test. The system is evaluated on mobike trajectory data in the city of Beijing and achieves an F1 score of 0.73 and a high ROC curve. The case study concludes that illegal parking is dependent on day, time, and locations. Some limitations of this system is that there is a lack of label data and the system is susceptible to external events. The solutions are mentioned in the bullet points. The second paper that I studied is mentioned here, and it aims to detect and report road surface conditions using mobile sensing. The main problem is that bad roads cause vehicle damage and endanger drivers and pedestrians. Therefore, Pothole Patrol aims to solve this problem by turning vehicles into mobile sensor networks with the help of a GPS and 3-axis accelerometers. The detection algorithm works by passing the accelerometer data through a series of filters as shown in the figure. And then the detections are uploaded onto the server where clustering-based filtering is done. The system was deployed in 7 taxis based in Boston, and to this, some sensor validations and training data was created. The system achieved a low false positive rate and detected 48 anomaly locations, thereby achieving high confidence. But this had some limitations like standard GPS error and missing data caused by drivers trying to avoid the potholes. The solutions for these limitations are mentioned in bullets. Thank you.